This section introduces the central language of calculus. We will estimate limits, decide when they exist, simplify difficult expressions, and study long-run behavior. Limits let us describe what a function is approaching without demanding that it ever arrive. Calculus grew from two problems: finding a tangent slope at one point and finding an exact area under a curve. Both require us to approach an answer through nearby approximations. Calculus has two famous doors, and limits have the keys to both. The position function tells us where an object is. Subtracting two positions gives displacement, and dividing by elapsed time gives average velocity. To find velocity at one instant, we shrink the time interval toward zero. A speedometer is basically doing limit-flavored mathematics very quickly. First, calculate the change in position and divide by the change in time. After expanding and simplifying, the average velocity is 30 plus 5h. The condition h not equal to 0 matters because an interval of 0 length cannot produce an average rate. The negative and positive h values approach 0 from opposite sides, and the velocities close in on 30. The interval disappears, but the velocity does not. That is the first limit doing real work for us. A limit is a statement about nearby function values. We can force the outputs as close to L as we want by choosing inputs sufficiently close to A. The phrase "but not equal to a" is crucial. Limits care about the neighborhood, not the address. Students often merge these two questions. The limit asks what outputs approach near A, while f of a asks what happens exactly at A. Sometimes they agree, sometimes they do not, and sometimes f of a is missing entirely. Same neighborhood, different paperwork. Direct substitution gives 0 over 0, but the nearby values tell a clear story. Values below and above 3 both approach 6. The function has a hole at 3, but the limit steps neatly over it. The undefined value at x equals 3 does not control the limit. What matters is the consistent behavior around 3. A tiny hole in a graph is not necessarily a mathematical disaster. Sometimes it is just a missing with excellent neighbors. These graphs show 3 different possibilities at x equals a. The function may meet the limiting value, be undefined, or have a different assigned value. In all 3 cases, the nearby curve approaches the same height L. The limit is remarkably unbothered by dot drama. Here the line passes directly through the point 2, 3. The nearby values approach 3, and the actual function value is also 3. This is the most cooperative case. Factoring shows that the quotient behaves like x plus 1 everywhere near 2, but the original formula is undefined exactly at 2. The graph has a hole at the height 3, yet the limit remains 3. Nearby points follow the line and approach 3, while the filled point assigns the value 6 at x equals 2. The graph answers both questions clearly. The limit is 3, but h of 2 is 6. The dot has changed jobs, not the limit. A two-sided limit requires agreement from both directions. If the left side and right side approach different values, there is no single two-sided answer. Think of it as a mathematical meeting. Both sides must agree on the destination. The graph approaches 1 from the left and -1 from the right. Because those targets differ, no two-sided finite limit exists. The two sides have arrived at different answers and neither one brought a compromise. The squared denominator remains positive and becomes extremely small near 1. Dividing 1 by a tiny positive number creates very large positive values on both sides. Infinity describes the direction of growth. It is not a real number destination. A finite limit can fail in 3 common ways. The two sides may approach different values, the outputs may grow without bound, or the outputs may continue oscillating without settling. In every case, there is no single finite target. Limits respect familiar arithmetic operations. We may multiply by constants, add, subtract, multiply, divide when the limiting denominator is non-zero, and pass through compatible powers and roots. The rules make limits behave almost like ordinary numbers, provided we respect the restrictions. Direct substitution is the practical result of the limit laws. When an elementary function is defined at the point being approached, substitute that value and calculate. This is the easy lane of limit problems, so enjoy it while the denominator permits it. Algebraic functions are constructed from polynomials using arithmetic operations, powers, and roots. Each example is continuous at every point in its domain, so direct substitution works wherever the formula is defined. The domain remains the bouncer at the door. Exponential, logarithmic, and trigonometric functions are transcendental rather than algebraic. Together with algebraic functions and their allowable combinations, they form the elementary functions. Direct substitution applies wherever such a function is defined. Each function is elementary and defined at the number being approached, so direct substitution gives the limit. Substitute carefully, simplify, and keep an eye on parentheses. Direct substitution is simple, but arithmetic still enjoys setting traps. At a point where a piecewise definition changes rules, the function value comes from only one rule, but the limit examines both sides. We must inspect both formulas and compare their trends. Piecewise functions require checking both passports at the border. This frame gives students the piecewise function and its graph. The rule changes at 1, so direct substitution alone cannot decide the limit. Give students time to compare what the graph approaches from each side. The left-hand rule approaches 3, while the right-hand rule approaches 4. Since the sides disagree, the two-sided limit does not exist, even though f of 1 equals 4. Direct substitution answered the wrong question very efficiently. Zero over zero is a signal, not an answer. It tells us that the visible formula hides the function's nearby behavior and must be simplified. When 0 over 0 appears, the algebra is asking for overtime. The goal is to uncover a simpler formula that agrees with the original expression near the target point. Once the obstruction is removed, direct substitution often works. We are not changing the neighborhood, we are cleaning the window through which we view it. Factoring exposes the common factor x minus 4. We cancel it only for x not equal to 4, which is sufficient for the limit because nearby inputs exclude the point itself. The algebra removes the disguise, and the limit turns out to be 8. The simplified expression x plus 4 is defined at 4, but the original quotient is not. They agree near 4, which is exactly what the limit needs. Cancellation cleans the formula, but it does not rewrite the original function's biography. The conjugate changes the radical difference into x minus 4, which cancels the denominator factor. The remaining expression accepts direct substitution and gives 1/6. Conjugates, turning radical problems into ordinary algebra since students first met square roots. The table shows the outputs exploding as x gets closer to 2 from either side. The square keeps the denominator positive, so both sides rise toward positive infinity. Infinity is not a number in the table. It describes the direction of unbounded growth. The numerator stays near positive 4. The denominator is a tiny positive number to the left of 3 and a tiny negative number to the right. The sides therefore head toward opposite infinities, so no two-sided limit exists. Same numerator, very different denominator moods. Zero over zero is indeterminate because many outcomes are possible after simplification. A non-zero numerator over a denominator approaching 0 is different. The magnitude generally becomes unbounded, and the sign must be checked on each side. Not all zero denominators belong to the same club. Limits at infinity describe what happens far to the right or far to the left on a graph. Infinity is not an input that we substitute. It indicates endless movement in a direction. Infinity is a journey, not a postal code. A fixed numerator divided by an increasingly large power of x approaches 0. This simple fact powers most rational function limits at infinity. The denominator keeps growing while the numerator stands still, which is not a fair race. The denominator has the higher degree. Dividing everything by x squared turns each numerator term into a reciprocal power that approaches 0, while the denominator approaches 1. The result is 0. The denominator wins this growth contest decisively. After division by x squared, the dominant term becomes 2x, which increases without bound. The remaining reciprocal terms vanish and the denominator approaches 1. The limit is positive infinity, so there is no finite horizontal limit. When the numerator and denominator have equal degree, dividing by the common highest power leaves the leading coefficients and makes all lower degree terms vanish. The limit is therefore 3/2. In the long run, the leading coefficients get the final word. At very large magnitudes, the highest degree term grows faster than all lower degree terms and controls the end behavior. For a rational function, replace each polynomial by its leading term and simplify the resulting power. The smaller terms have not vanished, they have simply become irrelevant celebrities. The degree difference predicts what remains after dominant terms are simplified. A negative difference gives 0, a zero difference gives the ratio of leading coefficients, and a positive difference leaves growing power behavior. Degrees are doing the heavy lifting, so we do not have to. Both polynomials have degree 3, so the cubic terms dominate and their ratio is 2. The direction toward negative infinity does not change the result because the same odd power appears in both numerator and denominator and cancels. The fixed cost contribution is 9,000 divided by the number of units. As production grows, that contribution approaches 0, leaving the $12 variable cost per unit. The fixed cost is still real. It is simply being shared among a very large crowd. For finite limits, remember that nearby behavior matters more than the value at the point. Direct substitution works for elementary functions in their domains. When 0 over 0 appears, simplify by factoring, combining fractions, or rationalizing before substituting again. At infinity, reciprocal powers vanish and dominant terms take control. Comparing degrees gives a fast prediction for rational functions, while the sign and direction determine unbounded behavior. One small word, limit, has managed to cover a very large mathematical territory. Limits teach us to separate exact position from nearby behavior. That distinction will soon let us define derivatives and instantaneous rates of change. Wisdom of the day. Getting close may not count in horseshoes, but in calculus it can define the entire answer.